Welcome to today's edition of Video Vision. This is about a recent discovery on the ASTEX upgrade Tokamak called the compact radiative divertor. So today I'm talking about something that was discovered on the ASTEX upgrade Tokamak not too long ago and published in a recent edition of the Physical Regulators journal, and it's called the compact radiative divertor. And I will explain the physics behind it and why this is potentially a great thing for future reactor type fusion machines. So to start with, I show you a German press release which sort of tries to bring this to the point. And what it says is, neue Technik ermöglicht kleinere Fusionskraftwerke, to be translated as a new technique will enable us to build smaller fusion power plants. Now this sounds really great. And as I said before, this is about the so-called diverter. So it's about how we get rid of the heat and the particles which come out of the plasma. So a diverter is something that we are using, a structure we are using to exhaust power and particles from the plasma. If you look again at the picture which was shown in the press here, there is this structure down here, so-called diverter plates, on which the plasma impinges and deposits heat and particles, and it is called a diverter structure because of the geometry of the magnetic field, which is not shown here, but in the next graph you will see it. There are in fact two ways how you would limit the plasma, or say get rid of heat and particles. On the left hand side is called a limiter. This was the case before the 1980s, where you would just put a material wall and you lean the plasma on the material wall. This red surface, which is the last closed flux surface, leans against the wall, is in direct contact with the wall. You would deposit there the heat and the particles. This means a large flux of energy to it, which you can take if you cool the thing well enough. But it also means that you will have erosion of particles of the wall material, which will enter the plasma directly, and they will then dilute the plasma in there. And to make this better, the plasma wall interaction better defined, what is then being done, and this is since the 1980s, that you do what is shown on the right hand side. This is a so-called diverter plasma. So you have an additional coil below the plasma here, which leads to this X point. So there is a geometry where the last closed flux surface is not in contact with the wall, but it is freely suspended in the machine, in the vacuum vessel, and then there are field lines outside, magnetic flux surfaces outside, which reach the diverter, so-called scrape-off layer, and along the field lines in these, the particles stream down into the diverter and deposit heat and particles there. Which means that now you have removed this direct contact of the core plasma, of the confined plasma, with the material, and in fact you have replaced this by the diverter configuration, which means that now you can follow along field lines on a long path down to the diverter plates. You can exchange temperature and density for each other, leaving the pressure constant in the plasma, saying that while the plasma itself, the core plasma edge, can be hot and not so dense, in front of the diverter plates you can make it really cool and also dense, such that there is a much more benign particle energy and there is a more benign erosion and plasma wall interaction there. So this is a great thing, and this is not only for the exhaust of heat but also of particles, because by baffling, by putting material structures, if you look again at this, there are material structures around, and it means you can build up neutral pressure of neutral gas in the diverter region, which then efficiently leads to pumping, because what you pump with the pump is of course neutrals and not charged particles. So this is all great, and this is about what I would say the textbook explanation of the diverter, meaning that you have to create this region down there, you have to create a sort of a separate chamber, you give up some of the volume of the vacuum chamber for the diverter region, and this enables you to exhaust heat and particles by pumping the neutrals. So what is now new about this compact radiative diverter? Well, actually, if you look at what it looks like, First of all, I have to say we have two diverter structures in the machine. One is up here, one is down here. By powering different coils, we can create the opposite of this in the upper part. So what I will show you is like a mirror image. So it will actually look something like this, and you will see the diverter and the X point on the upper part of the machine. So now I show you a picture of the compact radiative diverter. And in fact, what you will see if you look at it, there is hardly any diverter structure anymore. The X point sits very close to the target plates. In fact, on the right-hand side, it sits exactly on the target plate. So it looks like you have completely removed the diverter. So you might argue and say, we went around full circle, we invented the diverter, we found it great, and then we put it out of the machine again. But this is not true. First of all, you can see that the scrape-off layer, so there is still an X point, there is still a coil which leads to a 0 in the colloidal field here. You can see that the scrape-off layer, which is this red line outside of the closed plug surface, actually is dramatically increased in width here. So you still have a sort of diverted structure in here where you have a larger area, and also you will see that you still have this small region here and the region in here in which you can build up neutral pressure. So it is not going back to the limiter. It is still an X point, but the diverter structure has been shrunk to a very small volume. Now this works very well against what you would think, because you would think, okay, I make this very small, again I have now impurities going into the plasma, I have directly the hot particles impinging on the plates. Why it works so well is because we combine it with another effect, and this is, we learned that these are now, it's an experimental reconstruction of the radiation in the plasma. We have learned that if you put additional impurities, light impurities like nitrogen into the plasma, you will create extra electromagnetic radiation. What you see here is actually the radiated power per volume, and we manage, by controlling the injection of these impurities, we manage to radiate it away in all directions a lot of power. And so this is what is called an X point radiator, because it is sitting close to the X point. By this we cool the plasma before it hits the plates. So the idea is actually you first have to establish this X point radiator, again in the upper part of the machine. And then the next thing is that once you have this, you can do the compact radiative diverter. And I'm now showing you a movie. Again, here is the plasma, here is the X point, here is the strike lines, and then out there is the width of the scrape-off layer, which leads the power to there. And now you see in the movie how we run the experiment. We ramp up the heating power. It's 5, 7, 10. You see the power down there. It goes up to 15 megawatt once we are in the compact radiative diverter configuration, which is coming now. So now it's 15 megawatts. It sits very close to the target plates, and in fact there is not much happening. You can see that there is some heat going to the plates. It lights up. This is showing you the surface temperature, which you can see on the scale here, which goes up to 500-600 degrees. So it's nothing dramatic in there, but you always keep it under control. So with this, we have actually gone from establishing the diverter via establishing this radiative zone, the X point radiator, which takes care of distributing the heat, but not the particles, into 4 pi into all directions, to a structure where you only have a very small volume which is taken up by the diverter. The surprising fact was that the presence of the plasma is enough to baffle the particles, to hinder the particles going back into the plasma, so we can build up quite some neutral pressure, which is very good for pumping. And this is what would have been the expectation actually in the beginning. We would say, okay, I go back to more or less a limiter configuration. I will not be able to build up any neutral pressure there, so my pumping will be really poor. But by having still the X point geometry and these wide flux surfaces of the scrape-off layer, plus taking away the heat with the radiative diverter, you manage to really come into a very benign regime for getting rid of heat and of particles. And the final step is, what is this good for? Well, it's good for if you reduce the volume of the diverter, you reduce the volume of the plasma. So on the left-hand side, this is our Astex upgrade. On the right-hand side is a projection for the same toroidal field coil, the blue stuff here. So the same money you invest in the hardware of the machine, how you could dramatically increase the size of the plasma. So by doing so, you would actually go to something which has almost double the volume of the plasma, which would be very good for confinement and for producing fusion power. So, and this is what this news flash, which I showed you in the beginning, was about. It said that by doing so, you have the prospects of, for a given machine size and a given investment into the coils, increase the volume of the fusion plasma, or if you turn it the other way around, if you have a given volume, you can build a smaller machine around that volume. So that's great. And what are the prospects? Well, we found this on Astex Upgrade. We are now rebuilding the upper diverter of Astex Upgrade in order to be able to do better experiments on this. We will understand better the physics and consolidate this. And in parallel, we are studying how you would apply this in a fusion power plant. So maybe in the next year, the next version of a conceptual design of a fusion power plant, the demonstration reactor, might already feature such a compact radiative diverter, giving rise to more volume, allowing you to make the machine more compact. That's it for today. And as always, I'm happy if you put questions below in the comments. I usually check the comments to find out if something is really unclear, and then we can have a session where we respond to the comments or try to explain this even better. But for now, that's it. Thanks for your attention.